So now in this lecture we start from the third operation on Fibonacci heap. On the third operation it was meld H1 and H2. So what do we do? First thing is you merge root cycles of H1 and H2, and second you adjust mean age to be mean of H1, mean of H2, and take the mean of this. So that's the operation. So how much time does it take to merge two root cycles? I already told you, merging two cycles is order of 1, and this is also order of 1. So actual cost is order of 1. So let's see what is the amortized cost. So potential change, what is the potential change now for this operation? What is the potential change for this operation? The number of roots in the two basically remain same. When you take the potential, you have to take the potential of H1 and potential of H2, sum it up. That is the potential before you did this operation. So the number of roots remain same. So there is no change in Ti, and even there is no change in Mi, the mark. So that means potential change is 0. So again amortized cost is equal to actual cost, which is order of 1. So both amortized and actual cost. So this is actual is equal to amortized is equal to order 1. Both are same for this operation too. Now here is the first one, which is a little bit non-trivial. It's not that much yet. This is the insert operation, but as we have seen, insert seems to be a little bit expensive, at least for the heap operation. It was taking order of log n for the plain heap. So here I already said the amortized cost will be order of 1. So let's see, insert H x, where x will be inserted in H. So first thing what we do, create Fibonacci heap, F heap H1, which has a single node x, and second meld H1 with H. Just create one Fibonacci heap with H1 and then meld these two. So how much, again how much, so let suppose this one gives me the new heap, say H prime. So what is the potential of H prime? It is Ti minus 1 H plus 1, because now the root cycle has one more. Previously it was Ti minus 1 H plus this new root, so that is plus 1, and 2 of Mi minus 1 H. This is remaining the same. So potential change Pi minus 1 is what? 1, exactly 1. So again amortized cost is 1 plus actual cost, which is order of 1. So amortized cost is also order of 1. Actual cost also order of 1 in this case. So now comes, so this is the fourth operation we had. Now comes the fifth operation, which is the delete mean operation. So this is delete mean H. So let me recall. It means we have to delete the minimum element from the heap H and readjust the heap. So what do we do for this one? First, this is the first non-trivial operation actually, and this is really important. This operation is important. This is the operation where we readjust the tree a lot, and this operation pays for the other operations. So here it is, remove the node with mean key, minimum key from the root cycle. from the root cycle you remove this. Now the second one, what do? When you remove this particular node from the root cycle, what happens to its children? Children are also in a cycle. So basically take its children and put it in the root cycle. You merge the root cycle with the cycle of its children. Merge these two cycles into one now. So merge the root cycle with the cycle of children of the node. And third, this is important, while, so now what do we have? We have some more nodes in the root cycle. Now we go over the nodes of the root cycle, and whenever two nodes are having the same degree, we are merging into one. That is the link operation. If two nodes have the same degree, we use the link operation. One is made the child of the other. We go on doing it until unless there are no two nodes with the same degree. So here I am going to write, while two roots R1, R2 have same degree, do link R1, R2, end while. And the fourth one is adjust the minimum key. So let me just take an example for the third operation basically. So how the third operation is done. Alright. So third operation is the most important one, which I am going over now with an example. So what we do to implement the third operation, we use an array. Okay, so we use an array A, where AI, so what is the invariant? AI, so AI points to the node with degree I if it is vacant. Otherwise, so what we are doing? We are scanning the root nodes in the cycle. So whenever I see a root node, its degree say 5, I go and check A5. If A5 already has a pointer, I know there is another root with degree 5. So we have to link that node with this particular node, and we have to put it into A6. That's what we will do. It's vacant. Otherwise if A of I is occupied with root R prime, link R prime with R and try to place in R, sorry, not R, A I plus 1. Okay, so let me just tell you what does it mean? All these words, what does it mean in picture? So yes, I will go back to that slide later. So here it is. Suppose, yes.
They have only those nodes which are the root.
Right. It's a pointer only to the roots. Nothing else. So here is an example. So suppose this is the root cycle I have. So this is the root cycle. After merging the children of that node, that cycle to the root cycle, we have got, suppose, this cycle. Now what do? We scan, say from left to right. We are scanning in this order. So here is an A, the array A is here. So initially it is 0. It is pointing to this because its degree is 0, which is fine. Next one, again its degree is 0. So now I go and check A0. So this is 0, 1, 2, 3, 4, 5, 6. So I go and check A0. A0 is already occupied. So that means there are two nodes with the same degree and they have to be linked. So once we link it, the situation becomes this now. So this has to be linked with this guy. So what does it mean? Suppose this has a key value which is more than this person here, then this has to be a child of this root. So the situation becomes this becomes a child now, this remains, and now A2 points to this, sorry, A1 points to this, because now this one has one child. Okay, now we scan to the next one. Again this root has one child, its degree is 1, but again A1 is occupied. That means there are two roots with the same degree. We need to link these two. So the situation immediately becomes this. So this part is here. This has become the child of this node, which is this node. And you can see initially this one was having degree 1, now it has increased by 1. So now A2 will point to here. A2 is pointing to this node now. Now I go and check the next node. Its degree is again A2. So that means A2 is again occupied. So I need to merge, link, sorry, not merge, that link this node with this node, because both of degree 2. So immediately the situation becomes, after this, single node, and this is so this is the root, this is the node. I am assuming that this has a higher value than this value, otherwise this will be just child of this one, the way we have just assumed. So now this has degree 3. So now A3 will point here, and we have nothing to scan basically in this case. So this is the operation which I just told. So now go back to this, what I just told. So AI points to the node with degree I if it is vacant. If it is vacant, it's fine. Otherwise, if AI is occupied with root R prime, link R prime with R and try to place it in AI plus 1. Why did I say try to? Because you may not be able to place it in AI plus 1. You may have to do another link. But this is the operation. Okay, and it will be clear why do we do this very soon. Actually, this is the operation where you do some kind of balancing. Okay, now let us see what, after doing this, what is the cost of this entire operation. First, I assume let Dn be the maximum degree of any node in an n-node Fibonacci heap. Suppose we know the bound on Dn. Ultimately we will deduce a bound on Dn, the degree of any node in F heap after any operation. Suppose we know that is, say, Dn. Now can you tell me, first of all, after this insert operation, after doing this linking, how many places of A will be occupied at most with respect to Dn? Suppose initially it was n node heap, now I have just Dn plus 1. It cannot be more than Dn plus 1, because this operation is saying if any two are same, you link them. So after this operation, all the degrees must be distinct, and I have assumed n node heap can have any node of degree at most Dn. So there cannot be more than Dn degrees, and 1 plus 1, because that may spill over to the last one because of Merging 2, we need one more. So we cannot have more than dn plus 1 root nodes after this operation. Yes. I am assuming dn to be the maximum degree of any node in a F heap with n nodes. Now go back to the step 3 of linking these nodes. What did we do? Whenever two root nodes have the same degree, we are linking it. So after this operation, the roots which are remaining in the list must have distinct degrees. Otherwise, we have linked it. Must have distinct degrees. And I already assumed with n nodes it cannot be more than dn. I have now n nodes. So I cannot have more than dn roots with dn, sorry, initially it was at most dn. I may have to spill over by 1 because we merged the 1 and you remember degree was increased by 1. So that's why dn plus 1. Actually this plus 1 does not matter for us, but all the thing is that we have at most order of dn. Actually it cannot be more than dn plus 1. We can always say that. So the total root nodes is not more than dn plus 1. This one we will be using in our potential function, this fact. So let us see. First of all, what is our actual cost? Step 1 was what? How much cost does it take? The step 1? Order of 1. That is, remove the node from containing the minimum key. Then step 2 was again another order of 1, merging of 2 cycles. Then step 3, how much time does it take? It is Ti minus 1h, that is the number of root nodes before the operation, plus dn, because dn is the number of nodes in the children cycle of that node. It cannot be more than dn, and that guides the total complexity of step 3, because the Ti minus h plus dn is the total number of root nodes before you started this link. It cannot be more than that. So this is the cost of step 3, and step 4 will be nothing but you have to check all the root nodes after doing this linking and which one is the minimum, and that is, I already told you, this is not more than dn. So total cost, actual cost is order of Ti minus 1h plus d of n.
So please explain that again. Ti minus h plus dn.
So the third step.
Okay, if you go back, it is guided by the total number of roots present in the cycle after you have merged the root cycle with the children cycle of that node. Step 2, go to step 2, you merge the root cycle with the cycle of children of this node. So how many nodes you have now in the root cycle? Ti minus 1h plus d of n. And this step 3 is taking, every time is taking one root node and linking. Each link is order 1, so it cannot be more than this total number of root nodes initially it had after this merging. So it is Ti minus 1h plus dn. The total cost is this, actual cost. Now what is the potential change? The potential change, potential afterwards, how much? Afterwards, after you have done this operation, what is the potential afterwards? Is dn plus 1, that is our at most that many root nodes, plus we did not change anything about the marking. We did not say anything about the marking. So 2 of mi minus 1h, that is afterwards the potential. At most it is less than equal to. And before, potential before, how much? It is Ti minus 1h plus 2 of again mi minus 1h. So what is the change? Change in potential is, so potential change is dn plus 1 minus Ti minus 1h. That is the total potential change. It cannot be more than that. This is the at most. Now what is our amortized cost? empty cost now. As I told you, it is the actual cost which is order Ti minus 1h plus Dn plus this potential change which is Dn plus 1 minus Ti minus 1h. So this is order of Dn plus order of Ti minus 1h minus Ti minus 1 of h. I just broke it up. This one is order of Ti minus 1h, order of Dn, this 2 order of Dn goes here, and then I just take out here. Now, here is a trick. I can cancel this Ti minus 1h with this Ti minus 1h. You cannot do it straightforwardly because this is in the order term. So there is a constant here. So you cannot say, suppose the constant is say 5, you cannot cancel 5 Ti minus 1h with a single Ti minus 1h. But the point is, I could have used the potential function such that I increase the weight of the potential function that way. Instead of taking Ti minus 1h plus 2 Mi minus 1h, I just take whatever you have a constant here, take that constant, more than that. In that case, this will have a larger factor than this one. This is called scaling basically. I will be scaling this part. Yes. So if you go back to the definition of the potential function, what did we take? Ti minus 1h plus Mi minus 1h plus 2, right. Now instead of taking TIH, I could have taken say 10 TIH. So far nothing will be disturbed by this. But here, suppose since this is order of Ti minus 1h, there is a constant here. You tell me what is the constant. If you tell me 100, then I will go and fix my potential function. I will take the potential function as 101 Th. Right? So then immediately we will have 100 Th minus 101 Th. So this will be negative. I have that flexibility. You first tell me what is your constant here, I go and fix my potential function. Basically I am scaling up the potential function. The constant doesn't matter. So basically that means you can cancel out this Ti and this Ti minus 1h, and then this gives you order of Dn. In a straightforward manner you cannot do, but the logic I just said, so this is by scaling potential function. We'll be using this scaling once more, you'll see. But again, it's a matter of constants. I'll be choosing my constants once you fix up your constants of your algorithm. All right. Now, so you can see the amortized cost of this particular operation, delete mean, is guided by the maximum degree of any node. So we must have one bound on the maximum degree of any node. And that's what we will see, that this bound is quite good. It will be order of log n, and that's why this operation will be log n. So before I give you the bound on Dn, let us look at a little bit differently on this tree structure. What we are doing actually, this is called the binomial heaps. What it is? So far all these operations, how all these operations have created the Fibonacci heap. Either it has created a node from scratch, or one tree has been created by merging two trees in the manner which I just said. When 2 degrees are equal, they are merged into one. There is no other operation by which you can create a tree in the Fibonacci heap. So these are the only 2 operations by which you can create a heap order tree in the Fibonacci heap so far. So let us look at those tree structure. How does it look like? A single node is fine. If there are 2 single nodes, how is it created? One is made child to the other. If there are 2 of degrees 2, then one is made to the child to the other. So what is the next one? It looks like this, right? So the tree with degree 2 must be like this so far. Otherwise you cannot create a tree with the root degree 2. There is no other way. The only way you have created the heap order tree is this operation delete mean in the third step, and a tree from the scratch, which is the first one. So what is the degree 3? I must have this one as a child of one node whose child is exactly the same. So basically what do we have? We have this. So this one is there. There is another node with the same structure basically. Now you have these two with the same degree. You made one as a child of the other. So there is 1, 2, 3, degree 3 now. So degree 4 will be, this one will be a child of one root whose structure is already like this. This is the way it will grow. So these trees are called the binomial heaps. Okay, but look at the degrees of the node now. What is happening? So suppose I just list down the number of nodes and degree of root. So number of nodes 1. What is the degree? 0. Number of nodes 2, degree is 1. Number of nodes 4, degree 2. Number of nodes 8, degree 3. Numbers of nodes 16, it will be 4. So can you see? It is 2 to the power. 2 to the power, the degree is equal to the number of nodes. So if the number of nodes is n, degree is log of n. So as if the operation third step in the delete mean is as if balancing the whole tree properly. But this time balancing in terms of the degree of the nodes, because degree of the nodes are more important here, not the height of the tree. Now it's not the height of the tree which we are looking for, because our complexity is guided by the degree of a node. Okay, so this is actually called the binomial heaps. If the trees are built with this operation, this is called the binomial heaps. And in binomial heaps, degree of each node is order of log n. So far so good. But now comes the last and probably the most interesting operation, which is called decreasing a key. Now we start on decreasing another operation which is called the decrease key. Now this is the most interesting operation on Fibonacci heap. So what it takes, decrease key, it takes the heap age, it decreases the key value of x by amount delta. So what are the operations? Sub operation 1, first is unlink tree rooted at x. First unlink it. So the pointer to x has been given, you just cut it out from its root cycle. It's not root cycle, the sibling cycle basically. The second, decrease the key by delta. Third, add x to the root cycle now, original root cycle now. And fourth, okay, this fourth operation, you just for the time being assume that there is a cascading cut. I'll just tell you what it is later. Do cascading cuts. So don't bother about the fourth operation right now. Now here is an example. So suppose we have this tree, 3, 5, 4, 6, 2, say 12, and these two are in the cycle, and suppose this is 7, this is say 9, and this 5 has say another 6 or 8. Now after we suppose we are going to make the change 7 to 6 basically. So we are decreasing the value of the key value of 7 by 1, delta is 1. So what does it do? Ultimately the tree looks like this. 5, 4, 6, this is 3. Now this, so basically it is cut from here. This is cut from here, it goes to the root cycle now. So 2 and 12 was there, now this goes to the root cycle, 7 with 9 now. And 4 was, sorry, 4 was here already with 10, say, this is also 10, and 5 will be having only 8. So we cut it here, put it in the root. Now when I say do cascading cut, it means the following now. The problem with this operation is, now no more I can claim all the trees are binomial heaps. Because I have, like for 5, I have cut a part of it. So the probably the property has been violated. Okay. So what we try to do, we do not try to keep all the trees actually equal to the binomial heaps, not exactly equal, but almost binomial heap. What we allow for any node to lose at most 2 children, not more than 2 children. Once it loses more than 2 children, we do something else. Alright. So that's what is the cascading cut. So here is the cascading cut. What do we mean by cascading cuts? So let X be a node which becomes a child of another node at time say t. Now there are two things. The first time X loses a child after t, it is marked. Now the marking also is coming into picture. It is marked. And B, the second time X loses a child after t, we unlink X from its parent, basically cut from its parent and add it to the root cycle. So this is why it is called cascading cut, because you just see here, suppose X has been cut from its parent because it has lost 2 children. Now because of losing X, its parent might be losing this X for the second time. So that parent might have been cut again from its parent. So it can go up the tree. The first time one node X loses one child, it is only marked. It is not done anything else. But second time it loses another child, it is really cut from its parent. But this can have a cascading effect. So let me take this example, what I am saying. Yes, I will go back to that one later, but let's look at the example now. 2, 4, 5, 10. It has 2 children, say this is a 6. Say this is 7. 4 has say 8, 11. Say this one has 30. So now suppose we are changing this node 10 to 7. It has decreased. So once we do this, definitely it has been cut from here. And suppose these are marked. 5 is marked, 4 is marked. Suppose they have already lost one child by previous operations, so that's why they are marked already. The node 5 and node 4 are marked already. Now once you cut this 10 from 5, 5 is losing this child for the second time. What it means by cascading cut, we have to cut 5 from its parent again. But again 4 is marked already. So 4 is losing this child for the second time. So this is the second child it is losing. So that means 4 has to be also cut. So 4 is also cut from here. So this is the cascading effect. one cut of 10 is causing a cascading cuts of the tree. But only those nodes are cut which are already marked. No other nodes are cut. And when a node is always unmarked, when you have cut it, say 5 is cut from 4, then the node 5 will be unmarked and it will go to the root cycle. And also when a node is made a child of the other node in the step 3 of the previous operation, that time also it is unmarked. Actually no marked node can be there, because marked node only goes to the root, and that time you already have unmarked it. Which one you want to repeat? Right. So suppose 5 is marked here, right? So when I take 5 out of 4, it goes to the root cycle. Once it goes to the root cycle, it is unmarked. This one goes out. This mark goes out. It is unmarked. Because it is as if it is starting from fresh. So that's the rule of marking and unmarking, and this is the cascading cuts. So now let us see what is the actual cost of this entire operation. What is the actual cost of this operation? Definitely the actual cost is guided by how many cascading cuts you have made. Yes.
In the last problem, we are cutting one if it's marked, and we are cutting it, putting in the root cycle.
Right.
So in that case, but we are going away from the binary heap cycle. Suppose we again do the.
I told you, we will go a little bit away from the binary heaps. Not binary heaps, binomial heaps. But it's not too much, because we are not allowing for more than 2 children to be lost. That's why this is done actually. You are allowing a little bit, but not too much. So we are not restricting to only to binomial heaps. And probably your next objection will be, if it is not binomial heaps, why then the degree is order of log n. But what we will prove, even with this, the degree will remain order of log n. Alright. So what is the actual cost here? Let us look at it. First of all, if there are total number of C cuts, so suppose there are C calls, basically cascading cuts means there will be a recursive call. In the algorithm there will be a recursive call. Suppose starting from 10, how many calls are there? Cutting 10 1, cutting 5 1, cutting 4 1. There are 3 cascading calls. So suppose there are C calls of cascading cuts, including the first one. Then the actual cost is how much of delete min? Sorry, decrease key. How much is the actual cost? If you go to the algorithm, you will see how much is the actual cost in terms of C. Order of C only. Nothing else is done. This is the most time consuming step. So it is order of C. Now, what is the increase in number of roots? It's exactly C. For each call you will put it in the root cycle. So increase in number of roots is C, and decrease in marking. Now we are trying to see how many nodes are unmarked. So decrease in marking. So that is C minus 1. C minus 1 nodes are unmarked. Okay, and probably in the worst case, the last node you might have marked it. Like here, when 4 is lost, 2 will be marked probably. So probably you have increased marking by 1. Previously probably it was not there, now probably there is 1. So that means total, so decrease in marking is C minus 1. So it is decreased, so it is minus 1. So total decrease is C minus 2. So change in potential is, so actual cost is order of C, sorry, no. So this increase in roots, that is Ti, C minus 2C minus 2. This is the change in the marking. This is the change in the marking. It is decreasing, that's why it is minus now. And it is 2 times C minus 2. What it is actually 4 minus C. It is actually 4 minus C. So what is the amortized cost? Amortized cost is order of C minus C plus 4, which is exactly order of 1 if again you scale it up. This order of C and C cancels. If I scale again this potential function, I can take care of this constant here. Like again here, this will take care of it. So this is order of 1. Now you can see why this 2 was required. Because if there were no 2, I would not get a minus C here. And if there is no minus C, I cannot get it cancelled, order C with C. If there were no 2, only C was there, C will get cancelled, but there will be, so it will be 4. Sorry, it will be say 2. But I need 4 minus something C to take care of this order of C. So that's why this 2 was introduced in the potential function. So this is why decrease key operation is of the order of 1.
So then any number greater than 1 can you multiply it with?
Yes, instead of 2 we could have taken 3, 4, 5. Doesn't matter. Okay, now let me just tell you one thing is missing. Everything I have told you so far for the binomial heap, sorry, Fibonacci heap, but what is the maximum degree of any node? Because I told you that some of the nodes may not, some of the trees are not exactly binomial heap anymore. So I cannot claim that. So let us see. So first, for doing that, I need to, this is the claim. Let X be any node and degree of X is say K. Let Y1, Y2, Yk denote the children of X in the order in which they were linked to X from earliest to the latest. Then this is the claim. Then degree of y1 must be greater than equal to 0 and degree of yi is greater than equal to I minus 2. So what we did? We took a node X and it has several nodes y1, y2, say y1, y2, y3, and these are the, this is the ordering is such that y2 is after y1, y3 is after y2 was there with the node X. Then the claim is y3 must have degree greater than equal to 3 minus 2, which is 1. Can you see why it is true? Because the degree will grow by your third step there in the linking operation, and linking operation will always put same degree nodes as one child on for the other. So that's why this is going to be true. So the proof of this thing is, before yi became the child of X, before yi became the child of X, X had at least I minus 1 nodes, or X had at least I minus 1 children, because yi you are taking. So that means yi must have I minus 1 children when y at least when yi was joined to X. So I had I minus 1 children and we allowed one child to be lost after that. So it must be greater than equal to I minus 2. That's the proof. The proof is very simple. If you go back to all the operations what we did, the proof is immediate. for this. But this gives you the next, basically this is the next theorem. Let X be any node with degree X equal to K, then the number of descendants of X including itself is greater than equal to Fk plus 2. This Fk plus 2 will be greater than equal to some phi to the power k, where phi is, I will tell you all this, root 5 over 2. Okay, if those of you who knows this Fibonacci sequence, this should be very well known to you. This is the golden ratio. This 1 plus root 5 over 2, this is the golden ratio, 3 point something. No, it's not 3, something like 2 point something. Okay, anyway, what is the proof? Proof is, suppose Sk is the total number of descendants of X whose degree is K. Suppose that we denote it as Sk. Now what is S of 0? Degree 0? 1. S of 1, that is the node with degree 1. It has one child and itself, that is 2. Now I am claiming Sk is greater than equal to 2 plus I is equal to 2 to K S I minus 2. This is the claim. Thus, the total number of descendants with degree K must have at least this many nodes. Okay, you can see why this term is coming. It's coming because of the previous claim. It is S I minus 2. You take y1 and y2, you take out this y1. y1 is 1 and itself will give you 2, this value 2. Then y2 onwards they have degree I minus 2 at least. That means S I minus 2 I can recurse. This is a recurrence relation. Because of that claim you are getting this recurrence relation. So Sk is greater than equal to this, and then you can immediately prove that Sk is greater than equal to Fk plus 2. What is Fk? I am going to define the Fk now. F0 is 0, F1 is 1, Fk is Fk minus 1. This is a Fibonacci series. Fk minus 1, Fk minus 2 for k greater than equal to 2. This sequence is called the Fibonacci sequence. It is like 0, 1, then 2, then it is 3, sorry 0, 1, then 1, then it is 2, then it is 3, then it is 5, 8, it goes like that. So what do we get now? Sk is greater than equal to Fk plus 2. This you can prove immediately by induction. And Fk plus 2 is greater than equal to phi to the power k, where phi is 1 plus root 5. So what does it mean? It means a node with degree k has at least phi to the power k nodes. So what is its degree? Degree cannot be more than log of phi to the power k, which is k. So basically what do we mean? Degree k cannot, it has to be less than log of total number, that is n, with base phi. Because you have this Sk is your n is greater than equal to phi to the power k. N is greater than equal to phi to the power k from here. So k must be less than equal to log of phi. Actually there is a floor function. So this is order of log n. And that tells us that the degree remains order of log n. And every complexity we have so far seen, either it is amortized cost is order 1 or order of dn, only for that decrease delete mean operation, and that can be done in order of log. So that is why all these operations can be done in amortized complexity order 1. Yes? Greater than equal to 2 plus k. How did I get this relation? Okay, so go back to this previous claim. How does this node k look like? So this node has degree k. So this is say y1, y2, y3 up to yk, right? Now the claim was saying that yi must have total number of descendants more than equal to I minus 2, degree I minus 2, yi, right? So you take this node y1, 1, this node 1, 1 plus 1, 2, plus yi, sigma of yi. So I can, by recursive definition, what should be its size? Si minus 2. This should be S2 minus 2, S3 minus 2, because its degree is at least I minus 2. By definition, Sk is the total number of descendants of a node with degree k. So that's why this relation is coming here. So we finish the Fibonacci heap here, but I suggest that you go back home and look at all the operations. We have said a lots of things today. So you see all of them have to be put together into one place.